I'm Coach Pete of Math Coach Me. I provide math coaching and tutoring services, and I also provide free lessons at my mathcoach.me site. This is the seventh lesson in my trigonometry series. We're going to explore graphing the tangent and cotangent functions. Unique to my approach is the use of Desmos calculators like the one we're seeing here from the lesson. Desmos is an exceptional tool for learning about and exploring math, and particularly any visual math, and certainly trigonometry is a very visual math topic. Also unique to my approach is there is a online interactive version of this lesson at my mathcoach.me site where you can take the time to interact with these calculators. You can set the different angles and see why that angle in quadrant one is plotted in a positive spot on that tangent function. So you can ask and answer your own questions. Excellent way for learning about math. I do appreciate all likes and comments and follows, so please consider that. And let's get started. Let's take a look at graphing the tangent and cotangent functions. The description for this video does include a link to the online version of this lesson, or you can go to the mathcoach.me site, and then you can go to Lessons, and then locate this lesson here, Trigonometry 7, Graphing the Tangent and Cotangent. Many applications, like the sinusoidal wave functions, many applications for the tangent and cotangent functions, both in modeling natural phenomena like tidal waves, but also pendulum motion. Also a lot of applications in computer graphics as well. So in this graphic here, in this Desmos calculator, we're seeing the tangent function in purple, and we're seeing the cotangent function in this teal color. Very different from our sine and cosine functions. Certainly they're not bound, so they will approach negative infinity or positive infinity. So certainly not range bound, but there are some domain restrictions. So are these asymptotes that they will approach, but they will never reach. So let's explore that further. Now, just before we get into graphing the tangent function, let's take a moment to explore one of the identities, the quotient identity, which is a relationship between the tangent function and the other primary functions, the sine and cosine functions. So, as we know via SOHCAHTOA, the sine of an angle, sine of theta, is the opposite over the hypotenuse. The cosine of theta, the ka, is the adjacent over the hypotenuse, and the tan of theta, the toa, is the opposite over the adjacent. So tan of theta is opposite over adjacent, okay, the length of the opposite side over the length of the adjacent side, and I'm representing these with O and A for those two side lengths. And taking a look at sine of theta, so sine of theta is the length of the opposite side over the hypotenuse, O over H, and I can restate that. I can rearrange that so that the opposite length is equal to the length of the hypotenuse times sine of theta. Similarly, with cosine theta, which is the length of the adjacent side over the hypotenuse, that can be restated so that the adjacent side, A, is equal to the length of the hypotenuse, h, times cos of theta. So by substituting those two into this trig ratio, tan of theta is the opposite over the adjacent. So I can substitute for the opposite, from our sine of theta rearrangement. Opposite is h times sine of theta, h times sine theta, and adjacent, A, is equal to h times cos theta. And then, of course, I can cancel. H over h is 1, so I can just remove that, and I get the quotient identity. Tan of theta is equal to sine of theta over cos of theta, and its reciprocal version, cotan of theta, is equal to cosine of theta over sine of theta. Let's take a look at that in this Desmos calculator. In this calculator, I have a unit circle with a radius of 1, And I also have a theta angle, which is going from 0 to 360 degrees, and then it's going to repeat from 0 to 360 degrees. That's represented in the shaded area here. And at any point, I can stop this. Let me get it into a positive value so that all of our trig ratios are positive. And I'm going to stop it right around 2. Okay, close enough. So at this point here, for this angle, 64 degrees, my sine of theta is 0.899. My cosine of theta is 0.437. Okay, cosine is adjacent over the hypotenuse. Hypotenuse is 1. That's, a little less than 0.5. You know what, let's make it 60. Okay, so my cosine of 60 degrees is the adjacent side, 0.5 over the hypotenuse, which is 1 on our unit circle. Our radius is 1. So 0.5 over 1, it is 0.5. And our tangent ratio is the ratio of the length of the opposite side, which I've marked as sine theta, over the adjacent side, cosine of theta. And when you divide 0.866 by 0.5, we get 1.73. Okay, so that is our tangent ratio. But notice also I have a variable, a quotient variable q, which is equal to sine of theta over cos of theta. And that reveals this number, or resolves to this number, 1.732, which is exactly the same of tan theta. So my quotient variable q, sine of theta over cosine of theta, is equal to tangent of theta. And we can see that for any angle. I can move that to, let's go to 120 degrees, okay? So here, my sine of theta is 0.86, my cosine of theta is negative 0.5, and when I divide, okay, sine of theta by cosine of theta, I get minus 0.1732, and that's the same value that I'm getting for my tangent of theta. So once again, using the unit circle, we can prove for different angles that tan of theta, we can prove the quotient identity. Tan of theta is equal to sine of theta over cosine of theta. Now, one other way of proving it is through similar triangles. So there are two similar triangles here. They're both right angled. This one, this smaller one here, and this larger one here. Okay? So they're both right angles. They both share this angle, so this angle must be equal to this angle. So they're clearly similar. They look similar. And in this case here, I could, use the relationship or the identity in similar triangles where this length here, the length of this, which is marked as tan of theta, over this length here, which is 1 on my unit circle. You can see it's right at our unit circle. So tan of theta divided by 1 is equal to sine of theta divided by cosine of theta. So again, using similar triangles, I can also prove the quotient identity. Tan of theta is equal to sine of theta over cos of theta. When graphing the tangent function, it's useful to start with a table, as we did earlier with the various other trig functions we graphed. So we can fill out in this table theta values between negative pi over 2 and pi over 2, and tan theta values for all of those different angle sizes. So first off, one thing that's different is the period of the tangent and cotangent functions is pi, or 180 degrees, so just halfway around the circle, and then it repeats. So I can see that I'm plotting here from negative pi over 2, negative 90 degrees, negative 45 degrees, 0, 45 degrees, and then to 90 degrees. Okay, so one complete cycle from negative 90 degrees through 0, and then to positive 90 degrees. So I can plot all of those points. I can plug them into a calculator, and for 45 degrees, I can use a special triangle. Okay, so here's my 45, 45, 90 triangle, and the tangent ratio is opposite over adjacent, so 1 over 1 is 1, so I can see at 45 degrees, the tangent of 45 degrees is 1, so I can plot that point, and the corresponding negative 45 degrees is negative 1, so I can plot that point. So the key things when you're graphing the tangent function are, number one, draw in your asymptotes. Put a little light dotted line of where your asymptotes exist, and they are at negative pi over 2 and pi over 2, and then every pi radians from there, 3 pi over 2, 5 pi over 2, and so on, in both directions. So first plot those asymptotes. Then plot this very important point. So the tan of 0 is 0. Then plot tan of 45 is 1. Tan of negative 45 is negative 1. And that's about all you really need to plot this out. That will give you enough to get the shape. Okay, so you're going to be going through 0. Of course, like all of the trig functions, they just continuously curve. So that'll give you that continuous curve into here, and then it's going to approach that asymptote and get closer and closer and closer as it approaches positive infinity. But it never quite gets to that pi over 2 value for the function. Same in the negative direction. So from here, we're going to go through at negative 45 degrees, we're going to go through negative 1, and then it's going to slowly bend and curve, as it approaches negative infinity, as the function approaches negative 90 degrees. Okay, some properties of the tangent function. So the domain is all real numbers, but there are some exceptions, all of those places where there are asymptotes. So all of those odd integer multiples of pi over 2. Now the range is unbound. So unlike your sine and cosine function, which only exists between negative 1 and positive 1, inclusive, your range is unbound for your tangent function. So it'll go off into positive infinity or negative infinity as it approaches any one of those asymptotes. The period is 180 degrees or pi radians, and the asymptotes exist at all odd integer multiples of pi over 2. Once again, we can use the unit circle to better understand the tangent function and how it's graphed. We know that the tangent of an angle theta, tan of theta, is equal to the length of the opposite side divided by the length of the adjacent side. And we can also express that using the quotient identity. Tan of theta is equal to sine of theta over cosine of theta. So let's explore that using this Desmos calculator. Okay, here in our function list, I have this one here in purple. Function of theta is equal to tan of theta, so I'm plotting tan of theta. And I have a slider to change the angle. Okay, so I can change the angle and see where that particular angle is plotted on my tan theta function. And that's in radians, but I also have a conversion. So pi over 2 is equal to pi over 1 times 180 over pi. So a conversion of pi over 6 to 30 degrees. And we have the primary trig ratios, sine of theta, cos of theta, tan of theta. And I can see that the tan of 30 degrees is 0.5777. Tan of theta by the quotient identity is equal to sine of theta over cos of theta. And we see the same number here, 0.5777 for 30 degrees. So let me set this to 0 degrees. So that's clearly one of the key points when you're graphing this. So first you're going to want to, well, actually, what I have here is a expression to turn on my asymptotes at all at all odd integer values of pi over 2, pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. Okay, so using that for that. So once you have your asymptotes marked, you can mark some of the key points like 0 for theta equal to 0 degrees, well, the sine of 0, if we were to plot that, that's also 0. Cos of 0, well, cos of 0 starts up here and then it goes down to pi over 2. So cos of theta is 1, so tan of theta is 0 divided by 1 is equal to 0. So let's move that up. Let's go to 45 degrees. Okay, so sine of 45 degrees is 0.707, basically 1 over root 2. Same for cos of 45 degrees. Tan of 45 degrees, which is the opposite over adjacent. So basically sine of theta over cos of theta. Tan of 45 degrees is 1. Okay, so that's a key point to plot. So you plot that right there at 45 degrees and 1. And then moving on, we can see that as we get closer and closer to that asymptote, well, here, this should be undefined, but that's just kind of a rounding error. Okay, so at 90 degrees, the tan of 90 degrees is undefined. Well, sine of 90 degrees is 1, sine of 90, so it starts at 0, and then it goes up, and then it hits its maximum at 90 degrees, so sine is 1. Cos of 90 degrees starts at 1, goes down to 0 at 90 degrees is 0. So therefore, tan of 90 degrees is undefined. 1 divided by 0 is undefined, and that's why we have an asymptote, and that's why there's no longer a line joining, this point, to our function. It just doesn't exist. Our function does not exist at 90 degrees. Okay, so let's go in the other direction. Okay, so back to 0, and I'm going to slide this in the negative direction. So let me get to negative 45 degrees. So at negative pi over 4, negative 45 degrees, our tan of negative 45 degrees is plotted here at negative 1. So sine of negative 45 degrees is negative 0.707. Cos is positive. Think about that. Our cos is reflected here in this x value here, and that is on the positive x-axis, but our sine value, okay, cos theta, sine theta, our sine value for this point is on the negative y-axis, so that's why that's negative. So therefore, tan of negative 45 degrees is going to be negative 1. And we can see our function, as we go through 0, has gone from positive to negative. And it's going to be negative as we get closer and closer to negative 90 degrees. Okay, so as we approach negative 90 degrees, let's do it in the other direction. So here we are at negative 90 degrees, and again, our function is not plotted. Now let me try this just a slightly different way. I'm going to type in that this is negative pi over 2 plus 0.1. Okay, so slightly close, but a little less than negative pi over 2. And we can see that the tan of theta at negative pi over 2 plus 0.1, is around negative 10. Okay, if I round that to negative 10. And if I were to make this even smaller, okay, negative pi over 2 plus 1/100ths, then it goes to minus 99. So that got quite a bit larger. And, I can make this difference smaller and smaller and smaller, getting closer and closer and closer to negative pi over 2, and this number is getting larger. Okay, and now we're at negative a million, negative 999 million, negative a billion right there. Okay, so as we are approaching negative pi over 2, we can see this line. It looks like it's going right along the y-axis. Well, it's slightly off the y-axis. We just can't see it on this scale, right? And we couldn't see it on any scale because it would just be way too large, that graph, right? So basically, this is, approaching, this is approaching negative infinity. okay, as we get closer and closer to pi over 2, negative pi over 2. When we get there, the function is undefined. Okay, let's look now at graphing the cotangent function. So the cotangent is the reciprocal of tangent, 1 over tangent, and its ratio is the adjacent side over the opposite side. And expressed using the quotient identity, cotangent of theta is equal to cos of theta over sine of theta. So you'll want to plot some of these key values. Now at 0 and pi, we have asymptotes. We have the cotangent of theta at 0 degrees, cotangent of 0 is undefined, cotangent of 180 degrees is undefined. So a couple of things here. One is, like the tangent, the period is pi, or 180 degrees, halfway around the circle. Another thing, cotangent via the quotient identity is cosine of theta over sine of theta. Where is sine of theta equals 0? So imagine drawing the sine function, and now you're good at this, right? So you start at 0. Well, you're starting at 0. Sine theta is 0 at 0 degrees. So that's where you're going to have an asymptote for your cotangent function. And then going from here, it's going to reach its maximum of 1 here at pi over 2, and then it's going to start to go down and again reach 0 at pi, another asymptote, okay? So you're going to have an asymptote at every integer multiple of pi, okay? Pi, 2 pi, 3 pi, and so on, and also in the negative direction. Okay, so you're going to draw in your asymptotes. At pi over 2, the cotangent of 90 degrees is 0, so you're going to want to draw on that key point. The other key points are pi over 4, 45 degrees, and 3 pi over 4, 135 degrees. So at pi over 4, at 45 degrees, the cotangent is adjacent over opposite. It's equal to 1, so you're going to plot that point. And at 135 degrees, it's going to be negative 1. So you plot that point. And with just those points, okay, this point and at pi over 2, 0, and at 3 pi over 4, negative 1, you can start to draw the shape of your curve. It's going to approach negative infinity and get closer and closer to that pi asymptote, right, at 90 or 180 degrees. And in this direction, as it's approaching 0, it's going to get closer and closer and closer to infinity, okay, as it's approaching 0. Okay. Some properties of the cotangent function. So the asymptotes, once again, are at every integer increment of pi. So they're at 0, pi, 2 pi, 3 pi, and so on in that direction. Negative pi, negative 2 pi, negative 3 pi in the other direction. So you start with your asymptotes to define the limits of your cotangent function. The range is unbound, so as it approaches these asymptotes from one side or another, it's either going to approach positive infinity, approaching the same asymptote, 0. From the other side, from the negative side, it's approaching negative infinity, okay? So the range is unbound, all real numbers, and the period is pi or 180 degrees. So this Desmos calculator is plotting the cotan function. Okay, so f of theta, I'm plotting it in green here. F of theta is equal to cotan of theta. I've got a slider again to control the size of my theta angle, and I've got a conversion of that. So this is in radians, this is pi over 8, and that converts into degrees at 22.5 degrees. And I can see the cotan or the cotangent of 22.5 degrees is 2.414, and I can see that plotted here, at 2.414. And also I've got my asymptotes plotted, at every integer increment or integer multiple of pi, Okay, so 0, pi, 2 pi, 3 pi in both directions. 0, negative pi, negative 2 pi, and so on. So let's start out at 0 degrees, one angle of interest. So at 0 degrees, the cotangent of 0 degrees is undefined. And that's because the sine of theta, cotangent of theta, can also be expressed by the quotient identity as cosine of theta over sine of theta. Sine of theta at 0 degrees is 0. Okay, so that's what we have undefined. Moving up to pi over 4, another angle of interest. So at pi over 4 at 45 degrees, our cotangent is 1. Okay, so the adjacent side over the opposite side, those sides are equal, 1 over 1. We get a cotangent of 1. Moving forward to pi over 2. So at pi over 2, the cotangent of 90 degrees is 0. So we cross through the x-axis here. And then moving to, let's go to pi over 4 here, or sorry, 3 pi over 4, so 135 degrees. Now it is negative 1. So the cotangent of 300 or 135 degrees is negative 1. Okay, and we can see that in the quotient expression of that as well. So as we approach 90 degrees, or sorry, at 180 degrees gets larger and larger and larger. I'm going to change this. I'm going to remove this increment. I had an increment of pi over 8. So let's just slide it. Okay, and I'm going to change the scale as well. Okay, so as we are approaching 180 degrees, we can see that our cotangent ratio is getting, more and more negative, larger and larger, right? And, we can get it, even bigger, and it's going to approach 180 degrees, but it'll never quite get there. And interesting, as it crosses 180 degrees, let me see if I can get right to 180. No, kidding. But as it crosses 180 degrees, it starts coming down from positive infinity. Okay, so it approaches negative infinity as it approaches 180 degrees, never quite gets there. Function is not, it's undefined at that point at 180 degrees. On the other side of 180 degrees, it's coming back from positive infinity. Okay, so it just repeats over its 180 degrees or pi radian period. That concludes this lesson on graphing the tangent and cotangent function. I do appreciate the likes and comments and subscriptions, so please consider that. In the next lesson, we're going to take a look at the inverse function. This graphic is from the next lesson, so we're going to take a look at the functions where, like your sine function, you pass at an angle, it returns the ratio for that angle for the relative sides, the opposite over the hypotenuse. For your arcsine function or your inverse sine function, you pass it a ratio and it returns the angle. So we're going to take a look at that in our next lesson. I'll see you then.